Have you ever just stopped and, really wondered how our world gets to be so colorful? I mean, we see these incredible rainbows stretched across the sky after a storm, and on a clear day, the sky is just this perfect, brilliant blue. It seems so simple, but it's all thanks to the amazing physics of light. Today, we're going to pull back the curtain on these everyday wonders.
Okay, so let's just dive right into the big question. How can something that looks totally white, like sunlight, possibly hold all those vibrant colors we see in a rainbow? I mean, it feels like some kind of magic trick, but I promise you, it's pure science.
So, to unravel this mystery, we've got to get our heads around a key property of light called dispersion. This is the secret process that literally unlocks the colors hiding inside a single beam of sunlight.
Now, to understand dispersion, our #1 tool is the prism. You've probably seen one of these before, right? It's just a chunk of transparent material, usually glass, with these flat angled sides. And it turns out, this really simple shape is the perfect gadget for messing with light.
So what's actually happening when light hits a prism? Well, as a ray of light goes from the air into the glass, it bends. It travels through the prism, and when it comes out the other side, back into the air, it bends again. This whole bending process, this change of direction, has a name. It's called refraction.
And this is where the magic really happens. That bending, that refraction, is the key. See, it turns out that not all colors of light bend by the exact same amount, and that tiny little difference in the bending angle is what forces the white light to split apart. This whole act of splitting white light into all its individual colors, that's what we call dispersion.
So, you see, white light isn't really white at all. It's actually a mashup of all these colors, what we call the visible spectrum. Each one of these colors is just a light wave with its own unique length, or what scientists call a wavelength.
Okay, this is the crucial part. A color's wavelength is what decides how much it bends. Scientists have a way to measure this bendability called a refractive index. So red light, which has the longest wavelength, has the lowest refractive index. It bends the least. And on the flip side, violet light, with its super short wavelength, has the highest refractive index, so it bends the most. This is exactly why the colors of a rainbow always show up in that same perfect order.
All right, so we've seen how a glass prism works, but what's that got to do with a rainbow in the sky? How does this same idea apply? Let's jump into our next section and see how it all connects.
The secret is, there isn't one giant invisible prism hanging up in the sky. Nope. Instead, after it rains, the air is full of millions and millions of tiny, floating water droplets, and every single one of those droplets acts like a perfect little prism. Inside every single one of those millions of raindrops, light is doing this beautiful little three-step dance. First, as sunlight enters the drop, it bends and splits into colors. Then, those colors bounce or reflect off the inside back wall of the drop. And finally, as they leave the droplet, they bend and spread out even more.
Now here's the final piece of the puzzle, and this is so cool. From where you're standing, your eye only sees one specific color coming from any one raindrop. But when you've got millions of drops, all at slightly different heights in the sky, they all work together. The drops that are at just the right angle, between 40 and 42 degrees from you and the sun, are the ones that beam that perfect arc of separated colors right to your eyes. And boom, that's your rainbow.
Okay, mystery of the rainbow. I think we can say that's solved. But that just brings us to the other huge color question about our world. And to answer this one, dispersion isn't going to cut it. We need a totally different way that light behaves. Right? It's the question every kid asks, and the answer is just fascinating. It has nothing to do with prisms or raindrops. Instead, it's all about a completely different way light interacts with stuff. And that principle is called scattering. So unlike dispersion, where light passes through something, scattering is when a tiny particle, like a molecule, actually absorbs light energy for a split second and then shoots it back out again, but in all different directions.
So picture this. A light wave comes in and hits a single atom in our atmosphere. The atom soaks up that energy, gets a little jolt, and then re-emits the light. But it doesn't just send it forward. It becomes this tiny little beacon, sending that light out everywhere.
So what's doing all this scattering? Well, it's the molecules in our very own atmosphere, mostly nitrogen and oxygen. And here's the kicker. It just so happens that these molecules are the absolute perfect size to grab onto and scatter light with shorter wavelengths, especially blue light.
Because blue light's wavelength is so close in size to those air molecules, it just gets bounced around like a pinball. It's scattered in every direction. But longer wavelength light, like red, is basically too big to be bothered, so it tends to just travel in a straight line.
That's why, when you look up, you're seeing all that scattered blue light coming at you from every part of the sky. And hey, this also explains why the sky isn't always that deep, rich blue. On a really hot, humid day, the air is full of bigger water molecules. These larger particles aren't as picky. They scatter all the colors of light more or less equally. And when you mix all those scattered colors back together, what do you get? A pale, hazy blue, or even a white sky. All right, now let's use this exact same idea of scattering to solve one final, absolutely beautiful mystery of our world, those incredible colors of a sunset. It really all comes down to the journey the light has to take. At noon, the sun's right overhead, so its light zips through the thinnest possible layer of atmosphere to get to us. But at sunrise and sunset, that angle changes everything. Now the light has to travel through way more air to reach your eyes.
So on this incredibly long trip through the atmosphere, the shorter wavelengths just don't stand a chance. The blue light, the green light, they get scattered away in every direction long before they get to you. The only ones tough enough to make it through that atmospheric marathon are the longest wavelengths, the reds and the oranges. And that's what paints the sky with those spectacular, fiery colors.
And you know, we owe a huge amount of our understanding of this to brilliant minds like Nobel laureate Sir C.V. Raman. His groundbreaking work on how light scatters really helped us get a handle on these amazing interactions between light and matter. You know, this quote about new instruments feels just perfect here. Because once you're armed with a new tool for thinking, like understanding dispersion and scattering, you unlock a totally new way of appreciating the world. You literally start to see these everyday things in a whole new light. So, the next time you look up at a blue sky or catch a glimpse of a rainbow, just remember, these two simple ideas, dispersion and scattering, are the artists painting your reality. And that should make you wonder, if this is all that's happening in just the tiny slice of light our eyes can see, what other incredible wonders are out there, hiding in plain sight just beyond our vision?